Swayam Prabha. Digital India. Educated India.
So we already know what is a Gaussian distribution and what is a Gaussian random variable, and now we want to say when we have a random vector, when we are going to call it a Gaussian random vector, what is the properties it needs to satisfy. So we already have for a single random variable, the PDF is given by so this means I have a Gaussian random variable x that has mean mu and variance sigma square. And what was its characteristic function? At a function u, how did its characteristic function look like? exp minus u mu, I don't know where was minus.
J mu u minus mu square sigma square by 2.
J u mu plus
Minus u square sigma square by 2.
By 2. This happened to be its Gaussian, it's a characteristic function. Now suppose I have a set of such random variables which are independent but not necessarily identical. So what I mean by independent, we already know what I mean by independent of set of random variables, right? We know that if their joint distribution splits into their marginal distributions, then we are going to call them independent. And I am going to say set of random variables to be identical if all of them have the same distribution. Okay. So now suppose I have a collection of random variables and all of them have they are independent. Then it so happens that you take any linear combination of these random variables, it is still going to be again Gaussian, maybe with a new mean value and a variance. Okay. So with this we are going to write it as a lemma. So take any m random variables that are independent and all of them are Gaussian random variables. So each may have its own mean and variance, different values. Now we are going to say if you take the linear combination like this, you understand linear combination, right? I will just take different weights, multiply each one of them with their associated weights and then add up. Then I got this linear combination. We are saying that this is also Gaussian random variable. So why this is true? So to see this, we are going to use the property that if a set of random variables are independent, then if you are going to look at the characteristic function of their joint distribution, that also splits into characteristic function of individual random variables, right? So that we have said. So we have said that a set of random variables are independent if and only if their characteristic function also splits. Not only their CDF splits, that also implies that their characteristic function also splits. So let's use that property, just quickly verify this. Suppose
Can we say that these x1, x2, xn are identical?
no, I am not saying that. I am just saying that they are independent.
But since they are all Gaussian,
Yeah, Gaussian, but Gaussian they could be with different mean and variance, right? They, for a given mean and variance, it is going to define different Gaussian distributions. It is a parameters. Okay. So now let's say I want to define characteristic function of my random variable x. Here x is now the joint collection of these random variables. So x is a vector here now, it is not simply a scalar. So now, okay, no, what I mean is, okay, now I'm going to define this x not, I'm going to define this x to be this linear combination. Okay, x is now again another random variable for me, it is not a vector as I said earlier, it is just linear combination of this, and I want to compute the Gaussian distributions, sorry, the characteristic function of this random variable x. Now what is this going to be? It is going to be expected value of e to the power j u and all this, right, a1 x1 all the way up to so this is nothing but expectation of e to the power j u a1 x1 into e to the power j u a2 x2 all the way to e to the power j u a n xn. Now that x1 x2 they are independent, do you think a1 x1 a2 x2 and an xn they are also independent? If x1 and x2 are independent, suppose x1 I multiply by a1 and x2 multiply by a2, will a1 x1 and a2 x2 will be also independent? So these random variables are independent. Now if they are independent, now can I write this expectation as the product of expectation of each of these terms? If they are independent, I should be able to do this. Now x1 is Gaussian, I know. Is a1 x1 is also Gaussian? A is a constant, right? So what is this quantity now? This is a characteristic function of what? a1 x1, and what it will be? So we already know that for a, if x is a Gaussian random variable, its characteristic function is going to just look like this, j u mu. Now, so it only depends on your mean value and the variance, right? So what is the mean value of a1 x1? Suppose let's say
A1 mu 1.
xi, expectation of xi is equals to mu I. For ith random variable which is Gaussian has mean mu I. So then what is this mu of this going to be? U
A1 mu 1 minus mu 1.
and it will be, what will be the variance of a1 x1? So if variance of, let's say, x square, I am going to denote it as sigma square, what will be the variance of a xi?
A square.
So then what is, then u square, and then I am going to replace sigma square here by
A1 square.
2, right? Or you can alternatively think of this as, like, instead of this as a random variable, you can think as this is u1, a1 is the point at which you want to evaluate this characteristic function, and for this random variable x. So in that case also, like, it is like same, like you are going to replace u by u a1 here, u by u a1 and u square by u square a square, or alternatively you can also think of a1 x1 as another random variable with new mean and variance. Now all the way to what is its value going to be? So now if I further simplify this, what this going to look like? It is going to look like j u summation a1 ai mu I minus u square summation ai square sigma I square divided by 2, right? Now if you now go back, and we have already said that every distribution has a unique characteristic function, right? Now if you just look at this characteristic function, what is this distribution corresponds to? What is this characteristic? This characteristic function corresponds to which distribution? Huh? What parameters? Just so suppose, let's go, if I want to map it to this, suppose let's say this, I have to, if this is some mu and this is some sigma square, okay. Anyway, this is constant, right, and it will be exactly in this format. So then this is going to be a Gaussian with, so this corresponds to a Gaussian with what mean? And variance? This. So this is going to be another, so this means my x here, which is a linear combination of independent Gaussian distributions, is going to be another Gaussian distribution with mean like this and variance like this. So what it says is that what we have just showed is any linear combination of independent Gaussian random variables is going to be another Gaussian random variable. So now we are going to use couple of more definitions. So what I mean by here is, let's take a collection of random variables. You understand this notation xi, I belong to capital I. So I is the index set here. Here this index set is going to have finitely many values. They are said to be jointly Gaussian if every linear combination is Gaussian, and they are done if that, and they are said to have a joint Gaussian distribution. So what we just what we mean here is you are given a set of Gaussian distribution, sorry, set of simple random variables. If you are going to take any linear combination of them, and they should be Gaussian. If that is the case, then you are going to call this set of random variable to be Gaussian. You are going to call them as jointly Gaussian, and they are said to be have Gaussian distribution. So we have already said that if x1 this set of xi's happens to be each one of to be Gaussian and they are independent, we know this is already true, right? You take any combination of them, they are again going to be Gaussian. So here these set of random, if they are independent and Gaussian, they are again already jointly Gaussian. But let us say if some given set of random variables happens to satisfy this property, then we are going to call them jointly Gaussian. Then, and now when we are given a Gaussian vector, so this vector will have components, right? And then we just treat those components as these components, and if their coordinates, so when I say x is a random vector, it will have x1, x2, let's say up to xm, then these I can treat it as coordinates of this vector, right, as we discussed in the previous class. We can treat them as these components, and if these components happens to be jointly Gaussian, then we are going to call that random vector as simply Gaussian random vector. Okay. So this was obviously, so here we just said collection of random variables, but I can treat all this collection of random variables as a vector, right, in which this vector constitutes the components. Okay, now fine, when I have a collection of random variables, how I am going to denote its distribution? So if I have a random variable x, that is Gaussian random vector, so I am now starts using, instead of random variable, I am going to use RV for random vector here. It should be clear whether I am just talking about a random vector or I am talking about a random, sorry, I am just talking about a random variable or random vector. I am going to denote its distribution by mu and k here, and you will see that it just like it only depends on these parameters, and here mu is the mean vector and k is the covariance matrix. What is mu here? It is like mu1, mu2 all the way up to mu n. So let's say I have components, right? X is a random vector and it has some n components, let's say. Then this mean vector is nothing but the vector of individual components. And what is k here in the covariance matrix? It is going to be a matrix of covariance of x1, x2, x1 with itself, covariance of x1, x2 to covariance of x1, xn, and similarly x2, x1, and you can write all the way up to covariance of x1, x1. So what is this here in this covariance matrix? What is this diagonal implies? Yeah, so the diagonal contains the variance of each of the components. Okay. Okay, now I will just list down some of the properties of these Gaussian random variables, and we are not going to prove any of them. You should verify all these things yourself. Yes. Or Gaussian random vectors, or like for which we are going to say it is going to be, it has joint Gaussian distributions. Now let's say if xi, I have this collection of random variable has a joint distribution, then each of the random variables itself a Gaussian random variable. Is this true? Why is that? So I have a collection of random variable. I am saying that if it is jointly, it has joint Gaussian distribution, . then each of the random variables is itself is a Gaussian random variable. Why is that?
We have defined it like that.
So yeah, so if it is a jointly Gaussian distribution, by definition we want for every linear combination, right? So in this every linear combination, what I could do is, like I have to choose A1, A2 all the way up to AN. These are the weights, right? I can just choose A1 to be some non-zero value and set all the others A2, A3 all the way up to AN to 0. In this case, I need to satisfy that A1 x1 is Gaussian. But since A is essentially a constant, it is better that x1 is Gaussian in this case. So, and similarly for each of the components. So it must be the case that if the set of random variables has joint Gaussian distribution, each one of them itself is a Gaussian random variable. And this property we have already verified. I'll just write it for the sake of completeness. If yeah, right now I am not saying anything, right? Like you say you are given a set of random variables, and if it satisfies, if they are jointly Gaussian distribution. For that, our need is every linear combination should be Gaussian. That's the only thing. I'm asking anything like they're independent, identically distributed, or anything. Just applying definition. So suppose this xi's are each Gaussian and independent, then xi has a joint Gaussian distribution. This we have already shown, right? The second point. What we are saying is, if this xi's, this collection of random variables are such that each Gaussian and independent. Did we show this or not?
Yes.
If each collection of random variables, they are Gaussian and they are independent, and we have already shown that you take any linear combination of them, that is again going to be Gaussian, and then by definition it has a joint Gaussian distribution. The third property says let's say xi has a joint Gaussian distribution. And you are going to construct and let this yj be another set of random variables where j belongs to set j, So is the statement clear here? What I am saying is take a collection of random variables that has joint Gaussian distribution. Now what you do is you come up with another set of random variables, call them yj, j taking again value in some set capital J, where each of this yj itself is a linear combination of this xi's. Let us say you have x1, x2 all the way up to x10, you have 10 random variables that is jointly Gaussian distributed. Now let us say you take one linear combination of these random variables, you can take another linear combination. Like that, say you come up with 100 linear combination of this x1 all the way up to x2. Now this 100 random variables which I have denoted yj, now this yj's our claim is again has a joint Gaussian distribution. Does it make sense? This should be obvious, right? Because if these yj's are already linear combination of xi's, and now you further take any linear combination of this yj's itself, there will be another linear combinations of xi's, and that is Gaussian distributed. So any linear combination of yj then has to be Gaussian distributed. That is why this property already holds, and we are going to call it as jointly Gaussian distributed. So now the PDF of random vector n mu k. So let us say I have already said that let us say x is a random vector and its PDF I am going to denote it as it's a let us say I denoted it by this value, right, n mu k, where mu is the mean vector and k is the covariance vector. So how this value is going to be like. So this is just denoted a Gaussian random vector with parameters mu and k. Now the CDF of this Gaussian random variable, Gaussian random vector is going to look like so I am assuming that this random vector x here as m components in this. Okay, just say that x is x1, x2 all the way to xm. So we said that this is a Gaussian random vector where the mean vector is mu and the covariance vector is covariance matrix is k. Now if that is the case, then its CDF, one can write its CDF as this. What is here mod of k here means it is going to be determinant of this matrix k, and what I mean by capital T here, it is going to be transpose because this x here is a vector and mu also vector. What is this vector? This vector is the mean of all the components, and k inverse I mean inverse of the matrix. Okay. Now suppose let us see we recover our initial Gaussian distribution for a single random variable with this formula. Suppose x consists of only one component. Now what this formula will reduce to?
2 by 1 by 2.
So here in this case m is going to be 1, right? This is going to be 2 pi, and in that case what is k going to be?
Variance of x1.
So k is going to be a matrix with only one element in this, and what is that? That is covariance of x1 with itself, right? So that is going to be variance, and that is also square root, so this is going to be this. And now for a single random variable, this is like a scalar, x is a scalar, and x minus mu is now just the mean of that random variable. And what is k inverse in that case? Sigma square or 1 by sigma square? Because this is k inverse, right? That is going to be 1 by sigma square, and this is going to be x minus mu, and we have 2. And this is exactly x minus mu whole square divided by 2 sigma square. That we have for a single random variable. So please do take a look into the proof of this that is given in the book. So this proof comes from the eigenvalue decomposition of your vectors, eigenvalue decomposition of your covariance matrix. From that one is going to derive. Do take a look into this. Now this is one last thing I want to say. If x is n mu k, random vector where k is diagonal. Okay, so what we are saying is, suppose you take a Gaussian random vector which has this parameter mu and k, but this k is special here. It is such that its off diagonal elements are all 0. Only diagonal elements you allow it to be some values, but off diagonals are all 0. That so off diagonals all 0 means what here? No. We in terms of covariance, when we say covariance of xi and xj is equals to 0, we say they are uncorrelated, right? So all pairs of random variables are uncorrelated. If that happens, then these random variables are actually independent. So you remember in the last class we said independence implies uncorrelatedness, but uncorrelatedness does not imply independence. But it so happens that for a Gaussian random variable, uncorrelated also implies independence. And this is provided for this is Gaussian random vector. This need not be true for any random vector, but provided if it is a Gaussian random vector, then that is the case. So you see that like if I already have a model where my random variables are jointly Gaussian distributed and they are uncorrelated, then they already implies that they are independent. Okay, so this is like a much nicer property to have, because just by uncorrelatedness I directly get these properties of independence. Okay, the last one. Now how to compute the characteristic function? The characteristic function, as we said, it has some nice properties, right? That is it is going to be unique for a given distribution and vice versa. So here for the characteristic functions of so here the characteristic function of a n mu k Gaussian random variable, that is denoted as phi of x u. Here x is a vector and u is also vector, right, because I am talking about random vector here. So that is going to be defined as expectation of e to the power mu transpose x, okay, and then that turns out to be simply e to the power j mu transpose mu. So mu transpose, so what we are writing it as, mu is for us the way we are treating it is all column vectors. Mu transpose is going to be a row vector, and this mu is a vector of means which is column vector. So u transpose mu is going to be what? That is just one real number, right? And this is again and what is this quantity is going to be? So u transpose ku, k is a matrix, u is a column vector, so ku is going to be one column vector, and then u transpose that is going to give you just one real number. So this is you see that it has very much similar to what we get the characteristic of a Gaussian random variable, but in the Gaussian random vector it is just like you have to deal with the vectors, so that is why this transpose and the matrix has come there. Okay, so this is about this Gaussian distributions. As you see that the Gaussian distributions has some nice properties in terms of this characteristic functions, and also if they are uncorrelated it directly implies independence, and this helps in many things where when your model satisfies this, your analysis become pretty much tractable, because uncorrelatedness is directly guaranteeing your independence. When you have independence, all you need to worry about is the distribution of each of the random variables. If you have that, then joint distributions can be easily computed by just taking the product of these individual random variables, right? So I don't need to really define the joint distributions there. All I have to worry about is the distribution of each of the component random variables in that case.